All right, welcome to today's class. So we talked yesterday about the real zeros of polynomial functions. One thing I want to touch on really quickly I didn't get a chance to yesterday is the idea of intermediate value theorem. In fact, let's go ahead and just look at a specific example. So if we look at the example, f of x is equal to x to the fifth minus 1.8 x to the fourth minus 17.79 x cubed plus 31.672 x squared. Let's keep going here, plus 37.95x minus 8.7121. All right, so there is our weird-looking polynomial function. So because we have non-integer coefficients here, yesterday we talked about how if we have integer coefficients on our polynomial, we can use the rational roots theorem to come up with possible rational roots and then test those by using synthetic division. But today, because we have a polynomial that doesn't have that, that's not going to work so much. So the first thing we'll do is we'll go ahead and plug this into our calculator and get a graph of this to try and come up with guesses as to what the roots might be. So this is a rough sketch of the graph. You go ahead and graph it in your calculator and get it in the right viewing window. Then our polynomial function looks roughly like this situation right here. And what we'll notice is that it sort of looks like there's a 0 at -4, -1, and 0, and maybe just to the left of 3, or sorry, just to the right of 3, we have a situation where it just touches the x-axis and goes back up. But we shouldn't just look at our graph and automatically assume that that's true. What we can do, though, is we can confirm that there are zeros there by looking at our table in our calculator, which will show us, let's look at this one right here, just to yes, specifically we'll look at this 0 right here, just to make sure this one is actually at 0 and that there is, for sure a 0 there. And to do that, we're going to look at the table in our calculator here. So I've just drawn, I went to the table function in my calculator just to get y values that matched up with specific x values. So if we're focusing on this 0 right here, we see that at 0, the y value is also not 0. So we can tell it's going to cross there at some point, and we know it crosses by what I'm going to introduce now, which is intermediate value theorem. Which, to sort of put it in very untechnical terms, just says that a continuous function, which this one is, so a continuous function must hit all of its y values between any two x values. Between any two, I should say, just in general. Or any pair of y values. So if I look at any pair of y values in this function, if a function, right, for instance, this function right here, if it starts at -8.172 at 0, so at 0 it's actually below the x-axis. The scale of this graph makes it look like it's crossing, but it's really not. But it starts below the x-axis at 0, and then by the time it gets to 1, it's way above the x-axis, way up here. Started below, it ends up above. That means that every single y value between -8.712 and 42.32 has to get hit. Right, so that means one of those values that's between -8.712 and 42.32 is 0. Right, so we know that there has to be a place where y equals 0 between these two. Right, between x equals 0 and x equals 1. So somewhere in here we have to have a 0, a place where y equals 0. Because to get from here to here, it had to get to 0 at one point or another. And because it's a continuous function, intermediate value theorem applies, tells you that that actually has to be the case. So a guess might be for this one, if we know there has to be a 0 between 0 and 1, we could guess, it's not going to be very accurate, but we could guess that the 0 might be at x equals 0.5, halfway between those two values, right? That's just a very rare, very rough guess, which the graph doesn't really give us much sense of whether that's going to be true or not. We'll have to actually finish solving this in a second here. And when we do, we can go ahead and do that. So in any case, we know by intermediate value theorem that there must be a 0 between 0 and 1 because the function goes from negative to positive below the x-axis to above the x-axis. That means it had to cross the x-axis at one point there, which we can see visually, of course. We see that it crosses the x-axis, but algebraically or numerically we can confirm that with the table. So for this one right here, because we don't have integer coefficients, we can't really use synthetic division and the rational roots theorem to finish this up. So to finish this up, we'll just use the root finder in our calculator, which with actually, if you use the table function, you'll find that, or if we use the root finder in our calculator, we'll end up getting that x is going to cross at -4, -1. The one that we guessed was 0.5 turns out to actually be 0.2. And then this last one over here where it just touches and goes back up ends up being 3.3. So once again, using the root finder in our calculator, we find that the 4 intercepts are -4, -1, 0.2, and 3.3, right? Once again, we used our calculator, not synthetic division, because anytime you have non-integer coefficients, synthetic division and rational roots theorem doesn't really work. One thing of interest is you're looking at -1 maybe and saying, well, at -1 y wasn't 0, it was -1 times 10 to the -4. Well, what's happening here is your calculator is not being exact. -1 times 10 to the -4 is a very, very, very small number. And it's effectively 0, it turns out. The calculator is just not quite exact there. And so sometimes your calculator will lie to you or trick you and make you think this is not a 0, when in fact it actually is a 0 because it has a very small error in its calculation of what the value of this is at -1. It's not quite -1 times 10 to the -4. It's rounding to -1 times 10 to the -4 when it should really be exactly 0 at -1. So sometimes your calculator tells you lies. So anyways, that's just sort of finishing up section 4.5 about real zeros today from yesterday. And there will be another question about intermediate value theorem on the homework for tonight. That we really want to start getting into is the idea of complex zeros. Of polynomial functions. Talked about real zeros. What about complex zeros? So, complex zeros. First of all, what is a complex number? And we're going to use a really broad definition of complex here. A complex number is any number of the form a plus bi. So a number that we can write in the form a plus bi. So before we might have talked about complex numbers just being numbers that actually have an imaginary part, which is the bi part. That's the imaginary part, right? And then the a part is the real part. But some numbers are purely real numbers and other numbers are purely imaginary. But we're still going to refer to all of them as complex numbers from this point forward. So even a real number like 3, for instance, we could just think of as 3 plus 0i, right? It is still a complex number in a sense. So really, the definition of a complex number is any number that we've ever dealt with. So all numbers now are complex in our new definition of complex here. So even real numbers we're going to consider complex, and certainly pure imaginary numbers like the number 2i, which is really just 0 plus 2i, right? That's also a complex number. And then there's, of course, complex numbers that have both an imaginary and real part. For instance, like -2 plus 7i, right? That's a complex number that has both a real part and an imaginary part, right? So when I say the word complex number from this point forward, I'm referring to essentially all numbers in the number system that we deal with, right? Real numbers that are purely real numbers that are purely imaginary, as well as numbers that are a combination of both, such as -2 plus 7i. So that's what we're talking about there. And so it turns out that complex numbers can be zeros of polynomials just like real numbers are. And that leads us to a principle that we're going to learn today, certainly, and that is the fundamental theorem of algebra. Right, the fundamental theorem of algebra says a polynomial function of degree n must have n complex zeros. Right? So whether those zeros are purely real, purely imaginary, or a combination of both, a polynomial of degree 5 has to have 5 complex zeros. A polynomial of degree 4 has to have 4 complex zeros, right? And so that's really important, right? And then another theorem that relates to that doesn't have a name, but a theorem that relates to that says that all polynomial functions can be factored so all polynomial functions can be factored into a form of f of x equals some leading coefficient, but then x minus r naught times x minus r1 dot 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 x minus rn minus 1 times x minus rn, where r naught, r1, so forth, all the way to rn are all of the zeros of the function. Right? So what I'm saying is a polynomial can be factored into a bunch of linear linear factors here of x minus the 0 times x minus 0. And that's true not just for purely real solutions like 1 or 2 or 3, but it's also true for complex solutions as well, which we know from our experience with quadratics, that some quadratic functions have 2 complex solutions instead of purely real solutions. But they can all be factored like this no matter what type of complex solutions they have, whether they're purely real, purely imaginary, or otherwise. Okay? All right, so let's start looking at, what do these non-real solutions look like? And a good example to look at are our quadratic functions. So a good example of how we can sort of investigate complex solutions to equations are quadratic equations. And so, for instance, if we have the equation x squared plus x plus, let's say, 10. Whoops. Let's rewrite that really quickly here. So the equation f of x equals x squared plus x plus 10, right? If I want to find the zeros of that function, I'll set it equal to 0, and I can't factor it, so I have to solve it by using quadratic formulas. So I'm going to do negative b, which is 1, plus or minus the square root of b squared minus 4 times a times c That's very clearly, sorry, all over 2a. And that's very clearly going to give us a negative square root, so we get negative 1 plus or minus the square root of 1 minus 40, which is going to be negative 39 over 2. 39 is 13 times 3, so that's not really reducible at all. And so I'm just going to rewrite this as I square root of 39 over 2. And so we see we have two separate solutions. I could, of course, this is two separate solutions, right? I could write this as two separate numbers. These are both complex numbers. I could write it as it either equals negative 1/2 plus or minus, sorry, not plus or minus, because I'm writing them as two separate solutions, plus I square root of 39 over 2, or it could equal negative 1/2 minus I square root of 39 over 2. So we see in this case, and this is always going to be the case because of the way quadratic formula works out, if a quadratic function has imaginary solutions, those solutions are always going to be a conjugate pair. They're always going to be a conjugate pair because of how the quadratic formula works. Right, and so this sort of hints at what is going to end up being a theorem here in a second, which is that if there is one complex solution that has an imaginary part, then the conjugate pair must also be a 0. And so that's our next conjugate pairs theorem. Which says if A plus BI is a solution, or sorry, is a 0, let's say, is a 0 of the polynomial function P of x, right? And B has to not be equal to 0, by the way, then, because otherwise it would be a real solution, and real solutions don't have to have conjugate pairs that are also solutions. Then A minus BI must also be a solution. So essentially, they have to come in pairs, right? Right? You can't just have one imaginary solution to an equation. You have to have at least two, right? And there's a corollary to this, right? Which says that, well, what if we have an odd number? What if we have, let's say, an odd, like a cubic function, for instance, that we know has to have 3 complex zeros? Is there any way that all 3 of those could all be imaginary if they have to come in pairs? Yeah, so it's true that for any polynomial functions, right? For any polynomial functions of odd order, like a cubic or a fifth order or 7th order polynomial, there must be at least one real solution that has no imaginary part. There must be at least one real solution. All right, so that's a lot of theorems. Let's actually go ahead here and put this into practice and see how we can use all these theorems that we just developed here. So, for the next theorem, let's say, and this is an example that I'm going to have you guys work on, a polynomial function of degree 5, let's say, has the solutions, let's say negative I 2 plus 3I and 7. Or has, I should say, the zeros. Has the zeros, negative I, 2 plus 3I, and 7. Right? What are the other zeros? Or find all of the other zeros. Of the function. Using the two theorems there, or the theorems that we've seen so far, which were the fundamental theorem of algebra that says that in a polynomial function of degree n has to have n complex solutions, and also the complex conjugate theorem, which says that any complex numbers has to have a conjugate, or any complex solution of a polynomial has to have its conjugate also be a solution. So using those ones, how can we determine the other possible solution to this? First of all, how many total solutions should this have?
5.
Should have 5. We have 3 of them already. 2 of them are complex. So if negative I is a solution, what should also be a solution? I also needs to be a solution. And if 2 plus 3i is a solution, we also have to have
2 minus 3i.
2 minus 3i be a solution. So all of the solutions together would be negative I, or no, we'd just have to find the other two. But anyways, the other two are I and 2 minus 3i. And if we add those all together, that's 5 total solutions, and so we're done at that point. So that's how we can use it. If we have one complex solution, we know the conjugate must also be that solution. Now, the next question is, using the other way, I give you, let's say I tell you that a polynomial function f has the zeros 1 of, I'll say in a second. So 1 has zeros 1, 1, and negative 4 plus I. And the reason why I put 1 twice there is because the multiplicity of that is going to be 2. So we have to worry about multiplicity there. And the polynomial is degree 4. Also needs to be stated. So f is degree 4. I would like you to find that polynomial, find f. What would f be? Essentially find a formula for f, if you know what the zeros are. So I'll actually walk us through this one since we haven't done an example like this before. So to find f, first of all, we know that we have 3 of the 4 zeros, right? We have 1, 1, meaning 1 is multiplicity 2 here, and we have negative 4 plus I. What if negative 4 plus I is a 0, what must also be a 0?
Negative 4 minus I.
Yeah, negative 4 minus I must also be a 0. And so that gives us all 4 of our zeros there because it's a degree 4 polynomial here. And so using the factor theorem that we developed, that we saw last earlier in the section here, we could say that f of x could potentially be x minus 1 times x minus 1, which is just x minus 1 squared. I said we're going to have multiplicity 2 for this one, right? Times x minus negative 4 plus I times x plus negative 4 plus I. So we can actually, by multiplying all of these together, we can construct our degree 4 polynomial, right? And so we end up getting f of x is equal to x minus 1 squared. I'll just multiply that out. It's going to be x squared minus 2x plus 1, right? And now these two, I'm going to have to FOIL these out, right? So I'm going to be multiplying binomials by each other in a second here. So I'll end up getting x squared, and then the middle terms will be negative 4 plus I times x. And I'm going to distribute this negative sign here. So it'll give me positive 4 minus I. So I'll have plus 4 minus ix, and then for the outer terms I'll have negative 4 plus I times x. And then for my last terms I have to go ahead and FOIL out negative 4 plus I. Whoops, that don't need to be negative 4 minus I. It's the conjugate here. Whoops, I'm going to go back and just do this. And so what I'm going to do here is actually, that's negative 4 minus I. Oh, and this needs to be negative. Wow, I don't know what I'm doing here. Sorry, guys. Little mistake there. So this outer term actually should be plus, and I'm going to distribute that so I get just positive 4 plus I, right? And so I'll have plus 4 plus I times x, and then I have to go ahead and I have to multiply these together. And I'm multiplying for the last terms here. So positive times a positive, this negative is going to go away here. When I'm multiplying conjugate pairs together, I know the middle terms go away. So really, I just have to worry about the outer and inner terms. So negative 4 times negative 4 will be plus positive 16. And then I times negative I will give me positive 1, right? So that'll end up being 17. So if we go ahead here and we add this all up, and right here, if we're adding these like terms here, 4 minus I times, or 4 minus I plus 4 plus I is just going to be 8x, right? So we'll end up just getting f of x equals x squared minus 2x plus 1 times x squared plus 8x plus 17. Right? So we get a quadratic, which is what we would expect, and this quadratic is what's going to contain these two solutions, the negative 4 plus I and the negative 4 minus I. The two solutions to this are these two guys right here. So this quadratic right here contains the two complex solutions, right? And this quadratic contains the two real solutions. And then if I go ahead, now I'm going to skip all the intermediate steps here just for the sake of time and space. But if you go ahead here and you do polynomial multiplication here, multiply this by all three terms here, this by all three terms here, and this by all three terms here, and then you go ahead and you combine all of your like terms, what you'll end up getting is x to the 4th plus 6x cubed plus 2x squared minus 26x plus 17. And so, yeah, if we have a complex pair of zeros for a polynomial function, that means we'll have a quadratic that has those two solutions as a factor of f of x, right? This is an irreducible quadratic that is a factor of f of x. And that's always going to be the case. We'll always have an irreducible quadratic for every pair of complex zeros in a function f of x. And so we can construct a function that has these zeros just by multiplying all of these linear factors together here, right? So let's go ahead here and look at an example where we sort of put it all together here and use this to actually solve an equation. So if I have the function f of x equals 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18. I say go ahead and find all complex zeros of f of x. Right, and when we use the word complex, we mean not just ones that have imaginary parts, but ones that are purely real as well. So find essentially all of the zeros, whether they're imaginary or not, of the function f of x right here. All right, and so what you're going to do is, just like you did yesterday, you're going to use the rational roots theorem. Because these have because this has all integral coefficients here, you're going to use the rational roots theorem to identify all of the possible rational roots that you might have, and then you're going to go ahead and use synthetic division to test those to see which ones actually work. And you'll hopefully be able to reduce it down to the point where you can fully factor f of x. And then once you've done that, you should be able to get all of the zeros, including the real and imaginary zeros. So go ahead and take a crack at that right now. It might take a little while, but we'll take a look at it. All right, so to find all the complex zeros of f of x, first of all, there's going to be 4 total zeros, because this is a 4th order polynomial, so we need to end up with 4 zeros. The first thing we'll do is we're going to use rational roots theorem to say, okay, what are possible rational roots? Because this has integer coefficients, we can use this. And so if this does have rational roots, because there's integer coefficients here, they must be of the form p over q, right? Where p is a factor of the constant term and q is a factor of the leading coefficient. So possible values for p over q, well, first of all, p, all of our possible values for p could be 1, 2, 3, 9, and 18, right? Oh, sorry, 6. Gotta have 6 in there. 6 in there as well. Let's go back and erase that. So 1, 2, 3, 6, 9, and 18. So those are all possible values that the numerator of our solution could be, and the denominator, the possible factors would be 1 and 3. All the factor pairs of 3, all the factor pairs of 18, right? So let's just go ahead and construct them all. So let's say that if the denominator is 1, of course, then we could have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. If the denominator is 3, we could have plus or minus 1/3, plus or minus 2/3. 3/3 is 1. We already have that over here, right? Over here, so we don't have to do 3/3. 6/3 is 2. We already have 2, so we don't have to do 6/3. 9/3 is 3. We already have 3, so don't have to worry about that. And 18/3 is 6, which we already have. So the only two ones that have 3 as a denominator that we have to worry about are 1/3 and 2/3. The rest are fine. Okay? So what I usually do is we're going to go ahead and we're going to use synthetic division. We're going to make our big synthetic division chart here. And I start with the smallest ones, like -1 and +1. Don't have to put a plus there, though. -1, +1, -2, +2, -3, and so on. Hopefully we won't need to go that far. And so we go ahead here and list off the coefficients: 3, 5, 25, 45, and -18. And the last column is where the remainder is going to go, so that's the one we're going to be looking at. And so let's just go through here and see if any of these work. I'll do it in blue. So we always drop down the leading coefficients, so I'll just go ahead and do that for all of these, right? And so -1 times 3 is, -1 times 3 is -3, and 5 will be 2. -1 times 2 is -2, and 25 will be 23. -1 times 23 is going to be -23 and 45, which will be 22. And -1 and 22 is going to be -22, and -18 will be -40. So not a remainder of 0, so -1 cannot be a 0. So 1 times 3 is 3, and 5 is 8. 1 times 8 is 8, and 25 is 33. 1 times 33 is 33, and 45 is 78. It's just getting bigger, right? 1 times 78 is 78, and -18 is 60, so that doesn't work either. So those two we can cross off. -2, so we do -2 times 3 is -6, and 5 is -1. Negative 2 times negative 1 is positive 2, and 25 is 27. Negative 2 and 27 is negative 54, and 45 is 9. And then negative 2 and 9 is...
Should be negative.
Sorry, it's negative 9, thank you, because negative, yeah, it should be negative 9. Negative 2 times negative 9 is positive 18, and 18 is 0. So there we go, we found a 0 in negative 2. So what we're going to do, and we also have the depressed polynomial that we want. So what we're going to do is we're going to go ahead and write this in its newly factored form as x plus 2 times 3x cubed minus 1x plus 27x minus 9. I'll go ahead and do that in the next page there. Once we factored f of x using that depressed polynomial, we'll get f of x equals x plus 2 is a factor, we know, because we just determined that negative 2 is a 0. And then our depressed polynomial was 3x cubed minus x squared plus 27x minus 9. Now, what you could do here is you could repeat this whole process on this polynomial now, 3x cubed minus x squared plus 27x minus 9. Go ahead and repeat that process on that one, and then take the depressed polynomial and do this whole thing over again. Or you could look at this and say, ooh, I think there might be a, because some cubics are factorable through sort of clever methods, right? And this one actually is factorable by grouping. So what we can do is, from the first two terms here, we can pull out the x squared, leaving us with, I'll use brackets here. Whoops. Pull out the x squared, leaving us with 3x minus 1. And over here we can pull out the 9, also leaving us with 3x minus 1. Right, and then the 3x minus 1 can come out. Right, we have this common factor that we can factor out here. And then we have the x squared plus 9 over here. And so now we have two linear factors and one irreducible. This is a non-factorable or irreducible quadratic. And so what we can do is we can set each of these equal to 0 to find their zeros. So we know that the two real zeros are going to be negative 2. And then this one will give us 1/3 as a 0, right? And then for this one, we can go ahead and set x squared plus 9 equal to 0 and just solve this by doing x squared equals negative 9. And so x is equal to plus or minus the square root of negative 9, which that's just 3i, right? So it's plus or minus 3i. And so 3i and negative 3i are the two imaginary solutions there. So now we found all four complex solutions of this polynomial. Now, it is a lot easier because we have this grouping thing here. Once again, if we didn't have this grouping, we would have to repeat the rational roots process on this one to be able to find a root of this polynomial, factored out, and then we'd have that times the depressed polynomial from that. But in this case, we took a quicker route because of the grouping. But in most cases with the fourth order polynomial, we're going to have to do synthetic division twice in these cases. But in any case, we found all four complex solutions using all of the theorems that we've developed in this section. So the last thing I want to look at here is what is the implication graphically of complex or of imaginary roots? So normally we said that the zeros, right, of a function correspond to the x-intercepts of the graph, right? So if those x-intercepts, if they're complex numbers, what is true about those x-intercepts? Let's go ahead and graph this one right here just to see what it looks like. I'll do that in the next. We know, so we have the function f of x equals 3x to the fourth plus 5x cubed plus 25x squared plus 45x minus 18. And we note the zeros of this function we determined were negative 2, negative 1/3, or sorry, positive 1/3, 3i, and negative 3i. So knowing that, let's go ahead and we'll just use our calculator to come up with a graph of the function. Let's try and make that actually horizontal. So if we go ahead and graph this function, we see that it only has 2 actual x-intercepts right here. So anytime we have complex zeros, they contribute to no x-intercepts for the complex zeros that we have. So the only actual x-intercepts are at the real zeros. So complex zeros contribute no x-intercepts. So a function will have as many x-intercepts as it has real zeros. Right. And the real zeros will also tell you how many turning points there are, right? If I only have 2 x-intercepts, there can only be 1 turning point. If I have 3 x-intercepts, there must be 2 turning points. So there's always going to be 1 fewer turning point than there are x-intercepts. Always 1 fewer turning point than x-intercepts. That's how all this stuff relates back to the actual graph of the function, which of course is important as well. All right, that pretty much does it for today, so I'm going to go ahead and... So there's the assignment from today. The stuff from the bottom from page 238, this is from the new handout that I've emailed out to everybody. This is from this page 232 stuff is from the from yesterday's handout. All right, that's it. Have a great day, everyone.